In a high-rise building.
There was no warning.
At sea.
Innocent people died.
In a train.
Everything was on fire. Everything was burning.
Disasters can begin with the smallest things.
Changing the opening hours of a restaurant.
The bad glue job. A paperwork error.
Now, combining the latest research with every available source of evidence, experts will forensically analyze 3 disasters, down to each tiny detail.
You've really got to think outside the box.
You have to work your way back and understand each link in the chain.
State-of-the-art graphics reveal every critical detail at every critical moment.
This whole disaster could have been averted.
We can dissect them, get inside, or underneath, freeze time, and even reverse it. To conduct a complete disaster autopsy. Northeast Japan, March 11th, 2011. A massive magnitude 9.0 earthquake strikes just 45 miles off the coast.
This is the most powerful earthquake ever to hit Japan. It had actually shifted the Earth on its axis.
A giant tsunami hits the coastline.
The tsunami is absolutely devastating. Cars, boats, buildings, people are swept away. Over 18,000 people lose their lives.
But even then, the disaster isn't over. 150 miles north of Tokyo is the Fukushima Daiichi nuclear power plant.
This earthquake is an absolute disaster for the nuclear power plant.
Over the next few days, huge explosions erupt at Fukushima.
Now, as the news has come through of another nuclear explosion, we're being moved indoors. These are very nervous times.
4 of the plant's 6 nuclear reactors are destroyed.
Nuclear regulators give the Fukushima disaster a severity level of 7, the highest possible rating, and the same as the 1986 disaster at Chernobyl.
Prime Minister Khan calls for the immediate evacuation of about 100,000 residents in the area. They are left without homes and deeply fearful.
Now, using eyewitness testimony, scientific analysis, and photographic evidence from inside the devastated reactors, we will recreate the disaster. What really happened at Fukushima?
It would be easy to point the finger of blame here at Mother Nature. There was an earthquake. But the thing is that Japan has 5 nuclear power plants located in roughly the same stretch of coast. And only Fukushima became a disaster.
So there must be more to this disaster than just the earthquake. What is so special about Fukushima?
There are ancillary buildings, offices, workshops, but the main structures at the Fukushima plant are 6 nuclear reactors spread right along the coast.
Satellite images taken 3 days after the disaster show clear evidence of explosive damage. 2 structures are in ruins.
It's clear that these are reactor buildings. Reactor 1 is clearly damaged. Reactor 3 is a smoking ruin.
This is the core of the disaster. So why do these reactor buildings explode?
Fukushima Daiichi has boiling water reactors, which basically means that inside each unit, there's a giant steel tank, a pressure vessel. And inside the pressure vessel, there is nuclear fuel. And the nuclear fuel heats water, it becomes steam, the steam spins turbines, which generates electricity. So the critical thing to avoid is overheating. Because the nuclear fuel is constantly generating heat, it actually has to be cooled down, and otherwise, if it gets too hot, it will melt.
A core meltdown is a nightmare scenario that the plant is designed to avoid at all costs.
It's constantly having cold water pumped around it to remove the heat.
Plant data records that after the earthquake strikes, automatic safety systems shut down the reactors. But pumping cooling water remains essential to remove the vast amounts of residual heat still being produced. Data suggests this is where things begin to go wrong.
When the earthquake happened, Fukushima experienced loss of power.
The crucial cooling water is circulated by electric pumps. Without power, they will stop.
If the nuclear fuel isn't constantly cooled, you can get steam building up and up and up in the reaction vessel until eventually it becomes so pressurized that it can literally burst, releasing nuclear material out into the atmosphere.
Do the reactor vessels at Fukushima burst?
After the incident, TEPCO, the Tokyo Electric Power Company, which owns the plant, sends camera-equipped robots into the site to try to get a survey of the damage.
They provide vital evidence from inside the containment vessel.
So looking at the footage, we see that the containment vessels are actually still largely intact. There's no evidence of a steam explosion.
It is clear the reactor vessels have not ruptured. So what does cause the devastating explosions? Video evidence from the robots reveals another vital clue. The nuclear fuel in reactors 1 and 3 has actually melted.
Without pumps to replenish the water, the temperature inside the reactor starts rapidly rising to as high as 5,000 degrees Fahrenheit. This is not only hot enough to melt the fuel like the robotic footage suggests happened, but as well hot enough for a very dangerous reaction to start happening.
Without cooling circulation, the water surrounding the rods will boil into steam, and that creates a whole new risk.
The fuel rods are coated in zirconium, and that's important because in the presence of very hot steam, zirconium undergoes chemical reactions that produce hydrogen.
Could the Fukushima disaster result from a hydrogen explosion? Hydrogen is famously explosive, but only in the presence of oxygen. And there's none inside the reactor vessel. But plant records from the morning after the earthquake might help explain what happens. The pressure in reactor 1 has been climbing, but at 4 a.m., this suddenly changes.
When they measure the pressure in the reactor, the pressure has actually fallen since the last reading, but nobody's done anything to relieve the pressure, meaning that there must be a leak.
This means that before the first explosion in reactor 1, a pipe is leaking the contents of the reactor vessel into the building surrounding it.
With these ruptured pipes, they're not just releasing steam, they're also releasing hydrogen.
And in the reactor building, there is plenty of oxygen.
The hydrogen explodes, damaging the reactor buildings and leaking radioactive material into the atmosphere.
It is clear this disaster begins with the loss of electrical power to the cooling pumps. This causes a core meltdown, resulting in hydrogen explosions. But according to the design plans of Fukushima, losing electrical power shouldn't be possible.
There were a variety of backup systems, including diesel generators and batteries, to ensure that the electricity supply could be maintained even in the event of a power outage.
But plant records show that less than 1 hour after the earthquake, nearly all this backup electrical power has failed. How can these separate safety systems fail simultaneously?
So the plans of the Fukushima reactor complex show that the majority of the power systems were located in the basement of the plants. And this is for a good reason. They're there to protect them from earthquakes, ironically.
A lot of thought has gone into designing a plant that is earthquake-proof.
When they built the power plant, the engineers artificially lowered the ground about 80 feet such that it could be anchored into bedrock. This makes the plant more earthquake resistant.
So, the safety systems were effectively bolted to bedrock. But for coastal installations like Fukushima, earthquake damage is not the only risk.
At 3:36 p.m. on March 11th, a 50-foot high wave hit Japan's coast. And this is just minutes before the backup generators and the batteries all go down.
Ground level at Fukushima ends up just over 30 feet above sea level, and the backup systems are in the basement. So when the tsunami hits, the basement is submerged, destroying the emergency electricity supply. But tsunamis are a well-known risk on the Japanese coast. Why isn't the site protected? The Fukushima nuclear power plant is built on the coast because it requires lots of water for cooling its reactors.
The problem with putting a nuclear reactor on the Japanese coast is that that coast suffers extraordinarily from tsunami waves.
Images pre-disaster show that Fukushima is built with protective seawalls for exactly this reason.
When TEPCO was building the plant, they looked into the historic record to see how high they should build the seawalls to resist tsunamis. And they found that they would need to build it about 10 feet high in order to resist the big waves. To be extra safe, they actually added another 9 feet, building the seawalls up to 19 feet.
So why do these seawalls fail?
Oceanographic data showed 2 tsunamis hitting the coast on March the 11th. The first, at 3:27 p.m., is 13 feet high and is easily deflected by the seawall.
This photographic evidence shows the second wave. It is very different.
10 minutes later, the big one arrives. It's 3 times higher than Fukushima's sea walls, and it overwhelms the generators and the batteries.
Yet 4 other nuclear plants along the same coast avoid catastrophe.
The Onagawa nuclear power plant, which is about 75 miles north of Fukushima, was hit by a wave of the same size, but it survived pretty much intact.
Why is it only at Fukushima that tsunami defenses fail?
The designs for the Fukushima seawall were based on a tsunami that hit Japan in May 22nd, 1960, about 10 years before the plant was built. But that earthquake happened off the coast of Chile, and this is 10,000 miles from Japan. So the tsunami wave, by the time it arrived, was only 10 feet high.
Unlike Fukushima, the designers of other plants, like Onagawa, read Japan's centuries-long history of tsunami records in more detail.
The designers of Onagawa had looked much farther back in history for the design basis of their seawalls, to a tsunami that hit the coast in 1611 and another one that hit it in 869. Both of those tsunami waves were much larger than the 1960 tsunami.
Because of that, they build significantly higher seawalls. There is now enough evidence to piece together what happens in the Fukushima Daiichi nuclear disaster.
At 2:46 p.m. on March 11th, 2011, a magnitude 9.0 earthquake hits Japan.
The earthquake causes a loss of power at Fukushima and triggers an automatic shutdown. Backup generators kick in to keep coolant circulating around the reactor cores.
At 3:36 p.m., a 50-foot high tsunami breaches the seawalls around the plant, which has been built too low to protect it.
Seawater floods most of the backup generators and batteries located in the basement of the plant's buildings.
5 of the 6 reactors lose power.
Cooling water stops circulating around the active reactor cores.
Without this cooling, the cores continue to heat and pressure grows in the vessels surrounding the cores.
Temperatures rapidly climb, melting the fuel rods. Their zirconium coating begins reacting with the steam to produce hydrogen.
The highly flammable and radioactively contaminated hydrogen gas leaks out of reactors 1 and 3.
The leaking hydrogen explodes, wrecking the reactor buildings and shooting radioactive material into the atmosphere. It takes 2 weeks of hosing seawater into the reactors to stabilize them after the meltdowns.
The workers who stayed behind risked their lives to prevent an even greater tragedy, although a lot of damage had already been done. Over 100,000 people were displaced, and giant swaths of land were declared uninhabitable and unfarmable.
In the months following the disaster, European leaders decided on a new set of safety standards for nuclear power, and several countries decided to forego nuclear power altogether.
The disaster may have been triggered by a natural event, but it exposed human errors in its design that still haunt Japan.
There are many parts of the site that remain inaccessible to humans. It's simply too dangerous for them to go.
Fukushima was carefully designed to avoid the explosions that ultimately wreck it. But some disasters are caused by things whose sole purpose is to blow up. North Vietnam, Gulf of Tonkin, July 1967. Anchored 100 miles off the coast is the American supercarrier, the USS Forrestal.
We're talking about an aircraft carrier that is longer than 1,000 feet.
It is designed to project U.S. power anywhere in the world.
The vast hull can accommodate 200 aircraft, including an atom bomber capable of 700 miles an hour.
The Forrestal was making its first entry into the Vietnam War. Since arriving, she had made her presence known by launching wave after wave of attack aircraft from her 4-acre flight deck.
But on July the 29th, at 10:51 in the morning, the rear of the flight deck bursts into flames. Explosions rock the giant ship. Fires rage out of control. 21 aircraft are destroyed. 161 crew are injured. 134 are killed.
This is an unprecedented event. The most powerful military in the world has just lost its most effective weapons platform.
Now, combining detailed photographic and film evidence with eyewitness accounts and naval reports, we will digitally dissect the disaster. What wrecks one of the most powerful warships ever built? Using the available evidence, we can construct a timeline of the disaster on the USS Forrestal.
The crew were preparing for their second launch of attack aircraft that day, and the flight deck was absolutely packed with fully fueled aircraft, 2 of which had just taken off.
Surviving crew members placed the start of the fire at the rear of the flight deck, beneath 2 Skyhawk bombers, flown by Lieutenant Commander Fred White and the future Senator and Republican presidential candidate, John McCain.
Eyewitness accounts suggest that the fire started after one of the fuel tanks on the 2 planes ruptured.
Survivor testimony confirms that both planes are about to start a new bombing mission, meaning they are armed, and their fuel tanks are full.
Each Skyhawk can hold 400 gallons of fuel. That means there are now gallons and gallons of burning jet fuel on the flight deck. And the flight deck is crowded with explosives and missiles and other fully fueled jets.
One of the most vital sources of evidence comes from the ship's Plat camera, a manned camera system used to record landings and takeoffs. It captures the entire disaster on film.
The operator misses the start of the fire, but does manage to capture the crew grabbing their gear and racing off to fight the conflagration.
94 seconds after fire breaks out, there is an explosion underneath one of the Skyhawks. 9 seconds later, a second, more powerful explosion rocks the ship.
The explosion killed or maimed several crew members, including White, who couldn't escape his burning plane.
But the pattern of fatalities recorded in naval records reveals something striking. Despite the ferocity of the blasts, only 28 of the 134 crew killed are up on the flight deck. Why are so many killed below decks? Photographic evidence shows that exploding bombs create large holes in the 1 3/4 inch thick steel flight deck. And the deck has hundreds of gallons of burning jet fuel from the crippled Skyhawks running across it.
The gash in the flight deck allows the burning jet fuel to flow down and penetrate into other decks, causing new fires and creating huge volumes of toxic smoke in confined spaces, which is going to make it very difficult for people to escape.
Because the ship operates 24 hours a day, many crew are not even awake.
50 sailors died whilst they were sleeping in their beds.
In total, 106 people die below deck. But the Forrestal carries well-trained and experienced fire crews. Why don't they get the situation under control before fire pours down into the lower decks? Magnifying the flight deck footage at the start of the fire reveals a vital clue.
The man running towards the fire carrying an extinguisher is Chief Aviation Boatswain's Mate Gerald Ferrier. He was head of the damage control team on the Forrestal.
We can see Ferrier and his team rushing towards the fire, grabbing the foam hoses as they go in order to put the fire out.
The footage shows Ferrier clearly focusing his efforts with the extinguisher on one of the 1,000-pound bombs that's fallen off of the Skyhawk. So he had identified what the main threat was.
Experts have estimated it should have taken Ferrier and his team around 3 minutes to extinguish the fire.
That would get the situation rapidly under control. But just 94 seconds after the fire starts, the bomb Ferrier is spraying explodes.
The explosion kills Ferrier and most of the other experienced firefighting crew.
In an instant, the Forrestal has lost almost all its trained firefighters. The burning fuel now pours down below decks, with fatal consequences. Why didn't Ferrier realize the threat from the bombs and protect his vital team by pulling them back? Any bomb exposed to fire or intense heat has what is known as a cook-off time. This is the time it takes for the heat to cause an unintended explosion.
Ferrier and his team had watched training footage that demonstrated how a 1,000-pound bomb could be directly exposed to burning aviation fuel for several minutes before cooking off.
The footage Ferrier and his team had watched involved a Mark 83 1,000-pound bomb. It's quite a standard bomb for a Skyhawk. These are bombs with a relatively stable explosive and a very thick steel casing.
The training film says that in a fire, it will take at least 10 minutes for a Mark 83 to detonate. So why does it explode after just 94 seconds? Clues to explain why the 1,000-pound bomb on the USS Forrestal blows up so quickly, with such lethal consequences, can be found in the ship's records.
The day before, the Forrestal had been resupplied with 1,000-pound fat bombs, so-called because of their round shape.
According to naval records, some of these fat bombs are over a decade old. Their specifications are quite different to the bombs Ferrier is trained to deal with.
So while the Mark 83 bombs had a cook-off time of around 10 minutes, these thinner-skinned fat bombs had a much shorter cook-off time of around 85 to 120 seconds.
It is one of these fat bombs that kills Ferrier and much of his team. It explodes 94 seconds after the fire starts. It takes the decimated crew of the Forrestal 17 hours to finally extinguish the inferno. This all explains why the disaster is ultimately so devastating. But what triggers this lethal chain of events in the first place? Rewinding the plat camera to the very start provides a clue. At this point, it is filming in the opposite direction to the disaster.
Before the fire starts, there's a flash on the film. And this happens near one of the planes that is taking off.
At first glance, it seems the plane in the footage is firing, but magnifying the footage shows a curious anomaly.
The figure in the foreground actually looks the other way.
What is he looking at?
Closer examination reveals that this flash on the film, which is actually a reflection on the window that the camera is filming through, and that the origin of that flash is indeed the starboard stern part of the ship.
The flash traces back to an F-4B Phantom II on the rear of the flight deck. It is pointing directly at White and McCain's Skyhawks.
The Phantom is armed, amongst other things, with LAU-10 underwing rocket pods. Each pod contains 4 unguided 5-inch Zuni rockets.
The pilot, Lieutenant Commander Bangert, confirms it is one of his Zuni rockets that hits the Skyhawk's fuel tanks.
Bangert testified that he had not fired the missile accidentally, that all he had done is powered up the plane's electronic systems.
Launching a missile involves the pilot pressing a button on his joystick. This sends an electrical signal to the underwing pod to launch the Zuni. But Bangert says he never touches the launch button. All he does is switch the electrical supply from ship power to plane power, and the missile fires uncommanded. Later investigation of the F-4 Phantom discovers a design flaw. It can cause an unintended power surge during this switchover. A power surge that can activate the missile launch circuit. But an uncommanded missile launch should still be impossible.
Power surges happen, but there are several safety measures in place to ensure that they don't result in an accidental rocket launch.
A small pin inserted into a triple ejector rack under the wing physically breaks the connection to the missile launching system. With the pin in place, a launch signal cannot reach the missile.
According to normal procedure, that pin is only supposed to be removed when the plane is on the launch catapult, meaning if there was an inadvertent rocket launch, it would just fire off into the ocean.
However, naval records reveal that the Forrestal has implemented an unofficial procedure to speed up takeoffs. It involves removing the pin earlier. But even with the pin removed, a missile launch should still be impossible. An electrical plug called the pigtail must be physically inserted into the missile pod to arm it.
The pigtail is only supposed to be inserted in the last moment before the Phantom launches. So between the pin being removed and the pigtail being inserted, it should be impossible for the rocket to launch accidentally.
But naval records show that the pigtail procedure has also been altered.
It turns out that the weapons coordination board and the maintenance crew on board the Forrestal had changed the procedures in order to save time. They had been inserting the pigtail significantly before the plane was ready to take off. There are several eyewitnesses who testified that the pigtails had been inserted into Bangert's rocket pods prior to the incident.
We are now ready to bring all the pieces of the disaster together and reconstruct the entire sequence of events. The disaster on the USS Forrestal begins with a tiny procedural change to a missile launch system on a Phantom jet.
Ship's committee makes a decision to insert the pigtail significantly earlier than the original safety procedures dictated.
Evidence strongly suggests the pin on a second safety system has also been removed. An electrical surge is now able to trigger the uncommanded launch of a Zuni rocket. The rocket hits 2 Skyhawk bombers, puncturing at least 1 fuel tank.
The ruptured fuel tanks spread gallons of fuel onto the flight deck, which is ignited by the rocket's propellant.
The burning fuel engulfs bombs dropped by the Skyhawks. The bombs explode, killing many of the ship's firefighters and blowing several large holes in the flight deck. burning fuel floods through the holes into the lower decks of the ship, killing crew still in their bunks. It takes 17 hours to fully bring the fire under control. 134 people are killed.
The Forrestal managed to limp back to safe harbor in Manila before eventually returning to the United States, where it's going to undergo a $72 million refit.
After the Forrestal disaster, the safety procedures around the Zuni missiles were revised. Old bombs were taken out of service, and new bombs were given more insulation to protect them from the heat of a fire.
The Forrestal disaster begins with not following the design procedures. Procedural errors can kill, even when they are far from a battlefield. New York, a city of soaring skyscrapers and high-rises.
Originally, you have things like the Empire State Building, the Chrysler Building.
But New York is a city of constant change.
The skyline is dominated by cranes, which are constantly renewing a city that is ever climbing upwards.
From the early 2000s, there's a big boom in residential buildings being built by tower cranes.
On the corner of East 51st and 2nd Avenue, the construction of a residential high-rise is riding that boom. But on March 15th, 2008, the building's 179-ton tower crane collapses.
A crane falling to the ground, knocking down buildings, crushing cars.
The crane crashes into an adjacent building with the giant boom and cabin propelled across another building and landing on a house on an adjacent street.
It crushed at least one apartment building, damaged others, and sent people running for their lives.
Heavy metal work plunges 200 feet onto the New York streets.
There were 6 construction workers on the crane mast when it fell. 5 were killed, and the 6th was very seriously injured.
The operator and a victim in the building hit by the crane also die. 24 people are seriously injured.
This was a huge crane, and one eyewitness said that when it landed, it reminded him of what happened when the World Trade Centers came down, dust and debris everywhere.
Using eyewitness statements, engineering reports, and analysis of the wreckage site, we will digitally dissect the disaster. What causes this lethal collapse? The crane that collapses is known as a static tower crane.
A tower crane consists of a single lattice mast, a horizontal boom, and the operator's cabin just below that boom. It's a static system, meaning it doesn't move, and it's actually fixed to the building.
The collars and the tie beams lock the crane onto the building, providing the lateral support that it needs to stay in place.
The bottom of the crane is secured to a concrete base.
The crane legs sit on 2 large steel beams. Those beams spread the weight of the crane over 2 large reinforced concrete walls. So the base is designed to take the whole vertical load of the crane.
But photographic evidence shows significant damage to this base. Could the entire disaster be caused by a fault in the crane's foundations? The feet of the tower are displaced, but the design of the base is supposed to prevent this.
The feet of the tower are actually in pockets on 2 steel beams which span between reinforced concrete walls.
These steel pockets are designed to stop the legs moving sideways.
When we look at the foot of the tower after the collapse, you can see that the feet have actually moved out of those steel pockets, and the foot of the tower has actually moved towards the building. And that really shouldn't happen.
Photographic evidence suggests the steel pockets have not failed. Instead, their edges have been crushed. One face is bent and squashed inwards. For this to happen, the tower leg would have to lean sideways into the edge of the stationary pocket to crush it. This means the pockets and base don't fail. The crush damage is caused by the tower above moving. That should be impossible.
The tower itself is fixed to the building with the connectors at the 3rd and 9th floor.
Is there something wrong with the tower's ties to the building? To understand what has happened, we need to create a timeline of the disaster. Engineers confirm that prior to the collapse, the crane is bolted to the building at the 3rd and 9th floors.
The crane was involved in the construction of a 43-story residential building in Midtown East. Construction had already reached the 19th floor.
As the building grows taller, the crane has to grow with it. It is known as jumping the crane.
The jumping of the crane is an incredible process where you install a new section of the tower.
We know from survivors that at the time of the collapse, the 6-man crane team have just completed raising the tower by 54 feet. They are working up to 238 feet above the Manhattan streets.
The latest segment had extended the tower as far as it could go without fitting a new tie to the building. So the next job, once they jumped the crane, was to fit a new collar and ties on the 18th floor.
Evidence from the crane operators confirms the workers are attaching this 18th floor collar at the time of the collapse.
The first sign that anything was wrong was when huge pieces of metal started crashing down the side of the crane.
Photographic evidence of the 3rd floor level clearly identifies what these huge pieces of metal are. The collars holding the crane to the building.
What we see there is the collars that belong to the higher elevations is sitting on top of each other on the 3rd floor.
So you can see that the 9th floor collar sandwiched between the 3rd floor and the 18th floor collar, which is what was being installed at the time of the collapse.
How could both of these massive collars fall? Eyewitness evidence confirms that at the time of the 2008 New York crane collapse, the collar on the 18th floor is being fitted.
This is a huge collar weighing 5.5 tons in 2 pieces, which are connected around the tower.
This key photographic evidence is taken just before the collapse. It shows heavy polyester slings are temporarily supporting the new collar to the tower until workers connect it to the building with steel beams.
Before they could connect the tie beams to the collar, these slings snapped. This meant that nothing was really holding up this 5.5-ton piece of metal.
5.5 tons of steel slides 100 feet down the crane tower. It slams into the 9th floor collar. The force of the impact rips the 2nd collar away from the building. Both now plummet down onto the 3rd floor collar.
The 3rd floor collar doesn't completely break away from its connections, so that's why the 3rd, 9th, and 18th floor collars remain at that point.
There are now huge unbalanced loads on the tower.
There is a permanent 42-ton counterweight on the back of the boom. That allows it to lift much heavier weights.
The counterweight creates a huge imbalance.
And that's exactly why the tower is connected to the building to counteract that.
After the collars fall, the crane is only connected at one point, the 3rd floor. Above, 16 stories of unsupported tower are being pulled away from the building by the immense counterweight on the boom.
The crane tower was moved away from the building by the weight that is sitting on top. And it pivoted on one remaining connection that is on the 3rd floor collar.
The leverage of the 42-ton counterweight over 16 stories above is immense.
This created enough force for the legs to pop from their pockets.
Once that happens, the crane is doomed. The disaster is triggered by the failure of the polyester slings holding the collar on the 18th floor. How can these have snapped?
The crane manufacturer provides very precise instructions on how to lift the collars to prevent any potential errors.
Each half of the collar has 6 lugs, 2 are for lifting the collar and 4 are for securing it to the tower. It is critical that the correct ones are used for each job.
What should happen is that the 2 halves of the collars should be lifted by lifting lugs specified at the corners of the collars, and then secured thereafter using the lugs in the center of the collars.
This allows the securing slings to be tied to smooth supporting bars on the tower, designed for that purpose, while the collar is secured to the building. But according to the evidence, this does not happen.
You can see from a photo taken an hour before the collapse that one of those halves is actually being lifted by the central connections, not the lifting lugs at the corners.
It sounds like a trivial change, but the consequence is that the crane team secure the collar to the tower on the available lugs at the corners. Now, the securing slings cannot be fitted around the correct smooth bars.
They improvised and just connected the collar to the tower at those corner positions.
This improvisation creates critical problems.
The first is that there's only positions to fix the collar with 4 slings as opposed to the 8 specified in the instructions.
The collar is now held in place 180 feet above the New York streets by half the correct number of slings. And that's not the only error.
By connecting to the corners, they're being forced into sharp V-shaped grooves, which brings them into risk of cutting at the sharp edge. So you have fewer slings under a lot of stress being stressed over a sharp edge that gave them a risk of being cut.
Not only are there half the correct number of slings, but they are secured in a way that makes them vulnerable to failure. We can now piece together the evidence of the 2008 Manhattan crane disaster to identify exactly what happens.
The first in a series of errors that led to the disaster is the lifting of those collars by the wrong sets of fittings.
This prevents the crane's 5 riggers 200 feet up in the air securing the collar correctly, so they improvise. They secure it using half the correct number of polyester slings. They loop these weakened slings around V-shaped grooves on the corners of the crane. These pinch the slings and increase the strain on them. Before the riggers can attach the collar to the building, the polyester slings snap. The 5.5-ton collar falls 100 feet down the crane mast. It smashes into the collar on the 9th floor, tearing it away from the building. The crane is now attached to the building by a single connection at the 3rd floor.
At that point, we have our 42-ton counterweight at the top of the tower, pulling the tower away.
The one remaining connection on the 3rd floor collar acts as a pivot point. The legs of the tower dislodge from their supporting pockets. The 238-foot crane falls into the adjacent building. 7 people die in the accident.
The 2008 crane disaster prompted New York to change its regulations with regards to the safety of crane operation. Now, anyone involved in that has to take a 30-hour training course with refreshers every 3 years.
The legislation also limits the use of the synthetic slings, like the ones that snap. So hopefully, no one else will die again in this kind of disaster.